Okay, today we're going to look at sequences of transformations. And specifically, we're going to deal with quadratic functions. So we know that this would be the most basic form of what a quadratic function would look like as an expression. And each transformation that's added onto this thing will essentially turn it into what we call vertex form. And the nice thing about vertex form is that we can just look at the function and put it on the graph somewhere, right? It's the form of the quadratic that we have to do as little work as possible to get it to where we want it to be. So if you need a little bit more explanation on why A, H, and K are doing what they're doing in terms of how it's placing the graph, then I would recommend going back and watching a video that I posted where we explore each transformation individually and look at the ordered pairs of the function just to justify like why each transformation is actually doing what it's doing to the graph. But I'm going with the idea that you already have kind of a basic understanding of what each thing is supposed to do, and now we're just going to kind of put them all together and move forward from here. So, first thing, right, you're given a function. Even though we're looking at quadratics, we're going to take it in the idea that we have to recognize what it is that we're graphing. That way, if we're actually looking to graph a number of different things, we can still figure out what we're doing. So, since we have a function that has a square, we know that if we were to FOIL this out, we would have a highest degree value of x squared, which means we know the shape of this graph is going to be a parabola. So we know we're dealing with a quadratic function. And we recognize that it's in vertex form, so we can just do the transformations of each of these individually and put them on the graph where we want. Now, for starters, we know that a standard form parabola has its vertex at the origin, right? So basically, we're going to consider what each of these transformations is doing, and we're going to move the vertex point, which is the most prominent point on the graph, to its new location, and then build the rest of the function off of that vertex. So what we have here is any value that's attached to the x is going to affect the graph horizontally, or in the x direction. And we know that the transformation of -3 is going to be a shift of the graph, but it's going to be backwards from the way we would see it. We would normally think -3 in terms of x's would go to the left, but this is actually going to be backwards. This is going to move the graph right 3, and this is going to move the graph up 2. So I'm going to take this standard form parabola, which its vertex is at the origin. I'm going to move it right 3 units, up 2 units. Neither of these transformations is actually going to affect the shape of the graph. So once we get the vertex in its new location, we know that the rest of the parabola is going to be built in the same manner we would a standard form parabola. So we're going to use what we call what I'm going to call anchor points, in which we know that from a regular x squared, if I were to move out 1 unit, I know that 1 squared is 1. So if I go out 1 unit from the vertex, I'm going to go up 1 in either direction, because -1 squared is also 1. And if I go out 2 units, we know that 2 squared is 4. So I'm going to go up 4 units in each direction, because even -2 squared is 4. So these are what I'm going to keep referring to as anchor points. Once we move the vertex to its new location, I can still build the shape of the parabola off of these points, which are always moved from the new location of the vertex. And then we can just play connect the dots and get this shape of that parabola as we know it to be. All right, so let's try another one. Okay, so again, we recognize that it's basically an x squared function, so we know it's going to be a parabola. It is in vertex form. So we know that from the origin, which is where the original vertex is, this thing is going to be shifted or moved around. Okay? So for starters, we know that this +2 is going to be a horizontal shift. It's going to move it in the opposite direction as we would see it. So this is going to go left 2 units. This transformation is going to move the function down 1 unit. Now, we do have an a value in this one, negative. Now, this is still like a -1, if you want to think of it as a -1. So the a value isn't going to affect the shape of the graph because it's still a 1, but the negative in the front is going to be a reflection on y values. So a reflection on y values is going to be a reflection over the x-axis. So when we move our vertex to its new location, right? So left 2, down 1, right? This negative means that instead of going out 1 and up 1 for our anchor points, we're going to go out 1 and then down 1 in each direction. And then instead of going out 2 and up 4, right, we're going to go out 2 and down 4 because the negative is going to force it to be a reflection over the x-axis. So from where the vertex is, not the x-axis, from the vertex, when I go out 2, I'm going to go down 4. 1, 2, 3, 4. So since A was essentially a 1, the shape didn't change, but the negative reflects it. So it's going to be facing downwards. Now, technically, when you're doing these, there is an order with which the transformations need to be done, and realistically, it would be built off of order of operations, right? So if we wanted to do these very specifically off of order of operations, we would say that we would do this horizontal shift first because we would do what's inside the parentheses. Then we would take the a value, which will either reflect it if it's negative like this one, or do a stretch or compression, and then shift this thing up or down depending on what our k value is, right? But since the horizontal shift is always going to move it on the x-axis, if you want to think about doing this a value first, which is going to be a reflection, and then shift it to its new location, then we'll have it where it needs to be anyways. So let's try another one. Okay. Now, at first glance, you might say, well, this one actually looks like it's in standard form, which is ax squared plus bx plus c, which technically it is. Right? If b was 0, then this middle term would be non-existent, and you would have your ax squared value and your c. So technically it's in standard form, but even in vertex form, we can say that this guy is our a. Any value that's added or subtracted on the squared term would be your k, and then h would be a value that's either added or subtracted to x before squaring it, which we don't have. So realistically, we have this in vertex form. It's just that h is like a 0. So there's no shifting left or right here, but there is a shift down 5 units because this is our k value. And we know that this 2, since a is bigger than 1, it's going to visually be thinner, right? Because this would be what we would call a vertical stretch. If a is bigger than 1, it's going to stretch it vertically, and in terms of its shape, it'll actually be thinner than the normal parabola. So we're going to take the vertex from the origin, where it starts, and move it down 5 units. 1, 2, 3, 4, 5. Right? No horizontal shifting. And then we know it's going to be thinner. We're going to use those anchor points. Now, normally if I go out 1, I would go up 1. This 2 is essentially saying we're going to, whatever we go up for our y value, we're going to go up twice as much. So if I go out 1, I would normally go up 1, but I'm going to go twice as much as that, so I'm going to go up 2. Normally from the vertex, if I go out 2, we know that I'd go up 4, right? But I'm going to go up twice as much. So twice as much as 4 is 8. So 1, 2, 3, 4, 5, 6, 7, 8. So we can see that the parabola got thinner than it normally was. Oop, a little wonky over there. So it got a little thinner than the parabolas we were working with earlier. I mean, if you look at it, you can see it did get thinner, which is what we anticipated. But, how to make it thin, using those anchor points, it's 2 times the height that we normally would have moved, right? So as you can see, we're putting this graph together and not plotting any points. I mean, like with a table, like an XY table. We're not doing any of this. I don't want to do that. I don't want to do that if we don't have to, right? All right, let's try it out. Okay. So here, still in vertex form, there's no added value on the outside. So there's no K, right? No vertical shift. Well, there is a value that's added or subtracted inside with the X. So there is a horizontal shift. This is going to be backwards from the way we see it. So this is going to move to the right. Our A value is less than 1. So we know that visually this thing will be wider than the standard position. Right? If A is less than 1, we call that a compression. It'll be a compression, a vertical compression. Right? So if you compress this parabola vertically, it will make it wider, right? Because we're compressing it in this direction. So if I press it down, the parabola is going to open up this way. Right? So normal position, starting at the origin. This guy's going only right 1 unit. And then we're going to work with our half. Normally we would go out 1, up 1. I'm going to go up half as much. So half of 1 is just a half, right? I mean, if this is 1 and this is 0, half is right in the middle there in each direction. Normally if I go out 2, I would go up 4. I'm going to go up half as much, which is 2. If I go out 3, just to build some more here, if I go out 3, normally I would go up 9, because 3 squared is 9, but I'm going to go up half of 9, which is 4 and a half. So 1, 2, 3, 4 and a half. So I mean, if I wanted more of these kind of anchor points, then we can build them as we just keep going out. If I went up 4, normally 4 squared would be 16, but I want half of 16, which is 8. 1, 2, 3, 4, 5, 6, 7, 8. There we go. So if we connect these, we can see that our parabola has gotten wider than it normally would be. Right? And we used our A to compress the heights. Right? We compress the heights of these guys, which opens it up wider. Right? All right, let's try one more. So this one's a little different. Now, if you look at what we got going on here, we have 2 terms, right? A term is kind of a group of things that are multiplied together. So, I mean, I have the 3 halves times this whole group. This is all like one term, right? And then it's being subtracted from this 1, which is kind of on its own. So, basically, we have one thing minus another thing. Now, subtraction on its own, the order with which we subtract matters. But if I wanted to consider this like, this guy plus a negative, then we could rearrange where these guys are located. And I could say the negative 3 halves x plus 1, right? And then this guy is a positive 1. So if I add them over here, then these things are the same, right? I mean, it doesn't matter which one we put first and which one we put second, right? So we can see that if we have this constant kind of on its own, he's basically our K value. If I want to rearrange them, we could do that. So now that it's, looking more like a standard position of vertex form, right? If you want to rearrange them, nothing wrong with that. We can see that this is going to be a shift up 1. This one is backwards from the way we see it, so it's going to be shifted to the left, right? The negative, right, we can separate that from this 3/2, right? The negative is going to reflect, right? Because the negative is going to do something different than this guy. Now, 3/2, we got to be careful, because a lot of times what people will say is, well, fractions will make the parabola wider, and whole numbers will make the parabola thinner, but that's not the case, right? If the number is bigger than 1, then it will increase the height of the squared value. If the number is less than 1, then it will decrease the height of the squared value. So we know that this guy is going to make it thinner than it normally would be. Okay, so we got a lot going on, right? But we rearranged it, right, if you want, to see what each piece is doing from the original origin, which is where the vertex would start off for an x squared function. We're going to move it left 1, up 1, right? We know that the negative is going to reflect it, so instead of going out and up, we're going to go out and down. But we're going to treat this the same way. We're going to say whatever my height was, I'm going to multiply my height by 3/2, right? Or you can think of 3/2, if you want to do it in your head, as like 1.5, so you can kind of count it out as we're going, right? Either one. Okay, so we could say, if I go out 1, right, I'm going to go down, of course, because it's negative, and I want 3/2 the height, or 1.5 what I would normally move. So I'm going to do this just kind of off of the 1.5, and then I'll use the 3/2 in case you're not really following what I'm doing here. Okay, so if I go out 1, I want 1.5 times my height. So normally if I'm going down 1, because it's negative, I'm going to now go down 1.5. Right? Normally if I go out 2, I'd be going down 4, right? Because 2 squared is 4, but I want 1.5 of those. So 1 unit of 4 would be down 4, 1, 2, 3, 4, but I also want to go an extra half of 4, which is 2. 1, 2. So kind of again, I can say, well, 1.5 fours. So I want to go down 1 4, right? Because I want 1.5. I want 1 4 and half of 4. So I'm going to go 1 4, 1, 2, 3, 4, and half of 4, which is 2, 1, 2. Right? So it is a little thinner than it normally would be, right, as we can see. Again, if you didn't like this, you can say, well, normally, if we go out 1, we would go down 1, right? So whatever height we have, if we have a number that's a little harder to justify, I mean, 3/2 isn't that bad, but whatever the height is, we could multiply it by this a value to get a new height that we're moving. 1 times 3/2 is 3/2, or 1.5. So if I go out 1, I'm going to go down 1.5. So out 1, down 1.5. Right? Normally, if I go out 2 units, I would be going down 4 units, but we want 3/2 of this, right? So if I want to just multiply it by 3/2, I mean, multiplying fractions would be straight across. We could say 3 times 4 is 12, and 2 times 1 is 2, so half of 12 is 6. So if I go out 2, instead of going down 4, I'm going to go down 6. So out 2, remember, from the vertex, out 2, down 6. 1, 2, 3, 4, 5, 6. Right? So that way, if we had like some weird number like 7/3 or something like that, then it may not be quite as obvious, how far to go down. So we can just take how much we would normally move, multiply it by that A value, get your new movement. And then you can count out that movement from here. Okay? So again, we have it in vertex form. We should be able to just take this and plot the points off of our anchors. We shouldn't have to build a table, but nonetheless, if you ever forget in the heat of the moment, you can always just kind of pick some points and try to justify that you're in the right spot. All right?